Linda, dear, how do you turn this fancy contraption on?
It's already on.
Oh, I hereby command all of the scientific community to pay attention and learn about the sonic boom.
This message is approved by Mr. Simpson, Physics AP, 5th period.
Excuse me. So, let's start off by analyzing the basic properties of all waves. The wavelength is the distance from one point of a wave to another before the wave starts to repeat. The amplitude is the distance from the midpoint to the uppermost point or lowermost point of the wave. The crest is the uppermost point of the wave, and the trough is the lowermost point of the wave. Linda, fetch me the tea, dear.
We have no more, love.
Oh, whatever. So, let's go back to the waves. Let's, for example, assume that the period of a wave, or how long it takes to repeat, is half a second. The frequency of a wave is equal to 1 over the period. So, 1 over 1/2 will give us a value of 2 Hz. A Hertz is a main unit of frequency. To reiterate, the wavelength is the distance from a crest to the next crest, or the trough to another trough. So by now, we have covered all the basic properties of all waves. Now, let's dive into the speed of sound. The speed of sound is an important constant that you should all remember. 343 meters per second. What beauty. Linda, hurry up with that tea. Now, let's go into equations. The basic equation is velocity equals the wavelength times the frequency. There are many examples of waves that we will cover, some of which are light waves, water waves, and my personal favorite, hand waving. I swear I do not know who that guy is. And finally, sound waves.
Okay, now let's look at the sound waves. Now, if you ever had a rock be thrown in a lake, if you notice it has waves going around it in circular patterns, this is just like a sound wave, because when an object emits sound, the object emits a sound in a circular motion. Now let's pretend we have an ambulance, or anything that makes noise that moves. Now if you notice, if this ambulance were going to the right, the waves around it are a little different. Instead of being perfect circles, these waves are unbalanced. And on the right side, they have shorter wavelengths than the left side. Now if you're staying on the right side, this is going to change your frequency and how you hear the objects. Now let's go back to that original equation that we started off with. We have V equals F lambda. So if you're staying on the right side, the wavelength goes down, and the velocity is constant. Therefore, the frequency has to go up. That makes sense because you hear the noise louder. Now, if you're staying on the left side, it is the opposite. When you have the lambda go up, you have frequency go down because the velocity is constant. This makes sense because you hear a low pitch. Now let's look at the Doppler effect. The Doppler effect is an observed change in frequency when there's relative motion between the source waves and an observer. Pretty much means that the frequency changes in how you hear things. Usually this doesn't happen, but in this case it does because the velocity is constant and the wavelength changes. And this makes you hear a different pitch and a frequency. Now let's go back to the drawing board and see what really happens in simpler terms. So, the Doppler effect. I know it sounds scary, but it's not. So we know before, when an object is stationary, the waves are like rings around it because the object is not moving and the waves around it will be in perfect circles. It's kind of like when you throw a pebble in a lake, right? Because like when you throw a pebble in the lake, the waves around it, the water waves, actually make concentric circles. Now, let's go and let's try to see what happens when the object moves. Now, when the object moves, if you're on the right side, the wavelengths decrease, right? Because as it moves towards you, the next wave and the following wave gets shorter and shorter, right? But the velocity of the waves is still the same because the ambulance is emitting the same velocity of the waves. Therefore, something has to change. And when you have the old equation, V equals F lambda, you know that the frequency does increase just like an ambulance high pitch. Now, people still ask me today, even though the object is moving, how come the object's not creating sound in concentric circles? Now let's look at the diagram. So here's a thing on the left, typical wave, right? Two waves, equal distance. And as the object moves towards you, if you notice the wavelength decreases. and it gets shorter and shorter and shorter, like you see down below, to the point that they stack onto each other, and you see it here, and that's where the sonic boom comes in, because the waves add onto each other. Now, how do waves add onto each other? This is called constructive interference. So what happens here is that as the waves, let's say we have wave A and wave B. A is coming from the left side, then we'll just have B come from the right side. So as A goes to the right and B goes to the left, if you notice, what will happen? Well, what actually happens is that the waves add onto each other, right? It's like common sense, almost like a rope. When you have two pulses from two different directions, they add onto each other like this, and that therefore it makes a larger wave, larger impact. So constructive interference is when waves add.
Hello, loves, I'm back. 2 minutes you're off sipping tea and you got some random stranger doing your presentation for you. Anyway, let's talk about sonic boom. Here I am drawing the plane, and while it's not very good, please try to understand that it is only a rough sketch. As you can see, we will draw the sound waves around the plane, and they are going to form concentric circles. The sound itself is formed by the particles in the air hitting the edge of the plane, and this produces the sound that you'll hear. Sound is just vibrations in the air, and when they add up, that's what you hear. So these sound waves go in all directions, and that's what forms the sound that you hear. Now, let's form another plane, but this plane, let's say, is moving faster than the speed of sound. And if it goes faster than the speed of sound, we observe something very, very peculiar. Now, you see the particles here are also being deflected off the plane as the plane travels through the air. However, the plane also moves faster than the speed of sound. As you can clearly see, the particles themselves form this funnel shape around the plane, and the water vapor there condenses, producing the effect of what we see in a sonic boom. The sonic boom is also apparent in thunder and in many other situations. Now that you guys know this, you might be able to impress your friends, let's say. Here is my friend Indiana Jones. And he wields a very, very fancy weapon that produces the sonic boom. Indeed, it is the whip. The whip is thicker at the bottom and thinner at the top, so by the time the loop makes its way to the top, you have a sonic boom, since the whip is traveling extremely fast. Linda, I think we're done. How do you turn this device off? Anyway, here comes the sonic boom, folks. And now that you know, you can impress your friends and your lady friends, if you know what I'm saying.